Imagine, just for a moment, a universe where time isn't just a single forward-ticking arrow.
Hmm,
What if it had three dimensions, just like space? It sounds like pure science fiction, doesn't it?
it really does.
Yet, a claim like that recently sent, well, ripples through the scientific community.
It's an idea that, at first blush, really captures the imagination. It's got that novelty factor.
Absolutely. It's incredibly counterintuitive, but yeah, initially so exciting to consider. So our mission in this deep dive is to truly unpack this controversial claim.
Right.
We've meticulously reviewed a critical analysis of the original paper, and we're here to help you distinguish between, exciting speculation and truly rigorous scientific reasoning.
Yeah, separating the wheat from the chaff, so to speak.
Exactly. The goal isn't just to tell you what the science says, but why it says it,
Yeah.
and what this whole fascinating situation reveals about how science itself actually works. We'll delve into the core arguments presented, pinpoint the specific flaws identified, and
Yeah.
really underscore why discerning good science from, well, less rigorous science is so incredibly crucial right now.
And what's particularly alluring about the idea of three-dimensional time is its intuitive appeal, I think.
You think so?
Well, yeah, it offers a kind of symmetry with our three spatial dimensions, length, width, and height, which maybe on a superficial level feels aesthetically pleasing.
Right. You might think, okay, we have XYZ for space, why wouldn't time be similar? But what I found most surprising when diving into this was that physics doesn't build on what simply feels right or what looks nice on paper.
Exactly. That's not how it works. It's built on verifiable evidence, predictive power, and absolute logical consistency, not on what might seem intuitively balanced or beautiful.
So if we connect this to the bigger picture,
Yeah, one of the fundamental reasons time seems to have only one dimension lies in a crucial, observable asymmetry between space and time. They just behave differently.
that's a fascinating distinction. Can you help us visualize that? How spatial dimensions do affect forces in ways that time simply doesn't.
Of course. Think about fundamental laws like Newton's law of universal gravitation or Coulomb's law for electromagnetism.
Okay.
Both describe forces that diminish as the inverse square of the distance. So 1 over r squared.
1 over r squared.
Okay.
And in our familiar three-dimensional space, that makes perfect sense. Forces spread spherically outwards from a source,
Right.
and the surface area of a sphere scales with r squared. So the strength of the force dilutes as it spreads over an increasingly larger area.
Precisely. Now just imagine if we somehow lived in, say, 4 spatial dimensions.
Which we don't, but hypothetically.
Right, hypothetically. Then these forces would scale as 1 over r cubed. This illustrates a key point. Spatial dimensionality has direct measurable effects on how forces distribute.
Okay, that's clear.
But here's the critical part. Forces simply don't dilute or spread over time in the same way they do in space.
Okay.
This fundamental difference means time does not behave like space, and it creates a massive problem for any theory suggesting multiple time dimensions. The math just, well, it refuses to cooperate.
Okay, so time clearly behaves in a fundamentally different way from space. That seems like a big hurdle for the three-time idea. But what about other types of multidimensional concepts? Because you do hear physicists talk about more dimensions, and that's not always totally, off the wall, is it?
That's an excellent point for contrast, and you're right, it's not always nonsense. For instance, physicists regularly use something called a spectral dimension.
Spectral dimension. Okay, what's that?
This isn't about adding extra physical time axes to the universe or anything like that. Its purpose is more subtle. It helps analyze the effective number of dimensions particles move in.
Effective number.
Yeah, especially when studying really complex structures like fractals or within highly abstract concepts like, say, quantum geometries.
So it's more like a sophisticated mathematical tool to understand how things behave in certain weird situations, rather than a claim about reality having hidden extra time dimensions.
Exactly. It's a tool. It even allows for non-integer dimensions, like saying something behaves in 2.5 dimensions.
2.5D, how does that work?
It's abstract, yeah, but it's crucial sometimes in understanding complex systems or emergent physics. But, and this is absolutely vital, this legitimate concept, spectral dimensions, as profound as it is, does not validate the three-time theory, not at all.
Right.
Instead, it really highlights the vast difference between sound, even abstract, multidimensional ideas, and those that are, frankly, nonsensical.
Okay, so let's get into the nitty-gritty then. Turning now to the specific paper claiming 3 temporal dimensions. What were the most glaring scientific and mathematical errors that were identified? This is where the critique really bites, I imagine.
Oh, yeah. There were several fundamental errors, just basic stuff, really. First, the paper showed a profound misunderstanding of wave function normalization.
Wave function normalization. That's pretty core quantum mechanics, isn't it?
Absolutely fundamental. The paper wrongly attempted to normalize the quantum wave function in a spacetime with 3 time dimensions. It just makes no probabilistic or physical sense whatsoever.
Why not?
Because typically, the wave function is integrated over space to find the probability of a particle's location. And probability itself is conserved over time, not within time, if that makes sense.
Okay.
It's like trying to calculate the probability of something existing across different moments within time itself. It just doesn't align with how probability works in quantum mechanics.
So it's trying to apply a rule in a context where it fundamentally breaks down.
Okay.
What else?
It also contains what are known as uncontracted conservation laws.
Uncontracted, what does that mean?
It means their mathematical formulation didn't properly contract or reduce down to a single consistent value, a scalar. So the laws they wrote down simply didn't consistently show that fundamental quantities like energy or momentum were actually being preserved.
Which is kind of essential for any physical theory. Right?
Yes.
Conservation laws are foundational.
Foundational. If your laws don't conserve anything, they're not really laws of physics. On top of that, the author displayed a complete misunderstanding of Lorentz invariance.
Lorentz invariance. Okay, that sounds familiar. That principle is central to relativity, right?
Yeah.
Why is misunderstanding that such a huge misstep?
It's absolutely fundamental, yeah. It basically says the laws of physics are the same for everyone, no matter how fast they're moving at a constant velocity. It connects space and time in a very specific way defined by Einstein.
Okay.
To misunderstand Lorentz invariance is to fundamentally misrepresent how the universe itself is structured at its most basic level. It's not just some minor detail. It's like the bedrock of relativity and much of modern physics.
Wow. So wave function, conservation laws, Lorentz invariance, anything else?
Yep. And then there was a glaring error regarding the graviton.
The graviton, right? The hypothetical particle of gravity. What was the issue there?
Well, the graviton, if it exists, is theorized to be a spin-2 particle. This spin isn't literal spinning. It's a quantum property that dictates its fundamental nature, how it interacts, how it propagates forces. It's a tensor field.
Okay.
The paper completely misrepresented this, treating it as a much simpler spin-0 particle, a scalar field. It's a foundational error in quantum field theory. It's like mistaking a complex gear in a machine for just a simple round ball bearing. They behave totally differently.
It doesn't sound good.
Not at all. And perhaps most egregiously, the paper concluded with what could only be described as a meaningless dimensional reduction.
Meaningless dimensional reduction. That sounds bad.
Yep.
Vague and bad.
It is, indeed. The author claimed that 2 of these supposed time dimensions would somehow become negligible, just fade away, reducing the 6-dimensional spacetime back to our familiar 4-dimensional one.
Wow.
Exactly. What does it even mean for a temporal dimension to become negligible? There's no coherent physical explanation given. It's basically mathematical hand-waving.
So just brushing the inconvenient extra dimensions under the rug.
Pretty much. Mathematical gibberish, frankly. A way to try and force the theory back into matching our reality without any actual physics to back it up.
Wow. Okay, so with all these fundamental scientific and mathematical flaws, I mean, these aren't small things. How does a paper like this even make it to publication, let alone get any media attention? What went wrong?
Yeah, that's the other part of the story, isn't it? And it highlights a growing problem that we as a scientific community and maybe just as a society need to address more robustly. The paper was initially published in a let's say, low quality, perhaps less scrupulous journal.
Okay, so not a top-tier, rigorously reviewed one.
Definitely not. This is often a critical first step in how dubious work can gain some apparent legitimacy. It slips through a less rigorous peer review process, or maybe one that barely exists.
So it gets past that initial gate, even if it's a less guarded one?
Yeah.
Then what happens? How does it get out further?
From there, the university's PR office, presumably wanting to highlight their researchers' work, issued a press release. And they amplified the claim, probably focusing on the most headline-grabbing aspect.
The 3 dimensions of time angle.
Exactly. And as we've seen countless times, media outlets then picked up on that press release. Many likely just ran the headline or a lightly rewritten version without doing their own proper vetting or critical analysis of the underlying science.
The press release pipeline.
Yeah. It's a chain of events that, unfortunately, feels all too familiar in the age of instant information and clickbait. It really underscores how work that might be deeply flawed or even dubious can gain significant media traction.
And that can sometimes overshadow legitimate, careful research, right?
Right.
And just confuse people.
Absolutely. It muddies the waters and potentially confuses public understanding of science, which is never good.
It really makes you realize how much unseen rigor goes into every accepted scientific theory, compared to how easily a flashy but maybe unfounded headline can spread.
Mhm.
It brings us to a crucial point about, well, responsibility in this environment.
Exactly. I mean, while you might have some sympathy for the sheer effort that goes into writing any scientific paper, no matter how flawed.
Sure, someone put work in.
Right. But bad ideas, especially ones that misrepresent fundamental physics, must be publicly challenged, clearly and directly, especially when they risk confusing the public's understanding of how the universe actually works based on decades, even centuries of evidence.
So the definitive message for you, our listener, after all this digging, is pretty clear.
Absolutely unambiguous. No, time does not have three dimensions. The evidence just isn't there. Believing otherwise fundamentally ignores, well, pretty much a century of established physical theory and mountains of robust empirical data that confirms our standard model of spacetime.
Okay, so let's leave you with this to think about. In an age absolutely saturated with instant information and headlines designed to grab your attention, how does knowing the rigor and sometimes the profound lack thereof behind some scientific claims change how you evaluate surprising new ideas or research you see presented in the media?
Yeah, what's your personal filter? How do you try to distinguish what might be a truly groundbreaking insight from something that's just intriguing but ultimately flawed information? Something to ponder.